This is the next video in the chapter on advanced theories of bonding. We just talked about what molecular orbital theory is and how to differentiate the phases when we're drawing atomic orbitals. So now we're ready to look at molecular orbitals and what their features are. So molecular orbitals have many features in common with the hybrid orbitals that we made in valence bond theory. So similarly, molecular orbitals only exist between bonded atoms. You have to have a molecule in order to have bonds. One thing that's new here is that we're going to use all of the valence orbitals that we have available to form molecular orbitals. So when we're talking about valence orbitals, we're talking about atomic orbitals on a particular atom. So we're going to mix all of them. Once we start forming molecular orbitals, we are going to form molecular orbitals from all of them. There will be no atomic orbitals left. And just like for hybrid orbitals, the number of molecular orbitals that are formed in the blending process should be the same as the number of atomic orbitals that were blended together. This is a facet of group theory used to define the mathematics of this process. Over here, there are several features that are different from hybridization. When we form molecular orbitals, each of them is going to have a different shape. So that's one way you can identify which theory you're working in, because when you blend them together, they're each going to look different. They're also each going to have different energies. One of them is going to have a high energy, and one of them is going to have a low energy. And whereas hybrid orbitals are only used to form sigma bonds because they have excellent overlap on the internuclear axis, molecular orbitals come in all shapes and sizes. So we can use them to form sigma bonds, pi bonds, or non-bonds, orbitals that don't contribute to bonding whatsoever. So we're going to step through each of these different types of bonding, sigma bonding, pi bonding, and non-bonding, to look at what that orbital mixing looks like. But first, let's talk about orbital mixing in a generic sort of way so you can understand how these pictures we're going to draw are going to work. So when we mix two atomic orbitals together, we are going to have several options. We can either subtract the orbitals, or we can add the orbitals together. And these are where our different shape and different energy molecular orbitals are going to come from, depending on whether we add or subtract the orbitals. So if we add the orbitals together, remember that we use this Greek letter psi to represent a wave function or an orbital. So we can say if we take one atomic orbital and we add it to another atomic orbital, we square that whole thing, that gives us psi squared for a molecular orbital. And so in this case, when we are adding them together, this is called in-phase mixing, because those phases that we learned to draw in the previous video are going to line up. We're going to have the same phase overlapping with the same phase. And so this is going to form what's called a bonding orbital. And we're going to represent that with BO, because there are just a lot of names that we don't have time to write. So bonding orbitals are going to be the lower energy orbital in the pair, because bonding is going to be a stable interaction here. If you put electrons into a bonding orbital, it will strengthen a bond. So it creates that bond and it holds it together. And let's see. Another way of thinking of in-phase mixing is constructive interference. Remember when we talked about waves and how waves can mix with constructive interference or destructive interference, and how we said electrons are also waves? This is where that comes back. So the constructive mixing of the two wave functions forms a bonding orbital, a low energy, strong combination. Our other option is to subtract. So if we take one atomic orbital and we subtract the other atomic orbital, and we square that difference, that gives us psi squared for a different kind of molecular orbital. And that other kind of molecular orbital is called an anti-bonding orbital. And we're going to abbreviate that as ABO. So our anti-bonding orbital is going to be the higher energy one of the pair. Because remember that things that are high energy are less stable, and anti-bonding weakens a bond. So every time you add an electron to an anti-bonding orbital, it makes the bond weaker. And this is because it represents destructive interference, where the highest part of a wave overlaps with the lowest part of the wave, and the net sum is that they are canceled out. And so where the addition of the wave functions is called in-phase mixing, the difference is called out-of-phase mixing. Because you line up the different phases of orbital lobes next to each other. There's a lot of new terminology here. You might need a minute to sit and think on that to help keep track of it all. But there's sort of three ways of thinking about our two options. You can think about it as adding and subtracting. You can think about it as in-phase and out-of-phase mixing, or you can think of it as constructive and deconstructive interference. But however you like to think about it, just know that there is one low-energy bonding orbital formed and one high-energy anti-bonding orbital formed. So now that we have all the terminology out of the way, let's take a look at what the pictures of those orbitals look like when we draw them overlapping in phase and when we draw them overlapping out of phase. And we'll start with sigma bonding. Okay, so let's do the simplest type of sigma bonding first, which is to overlap an s orbital with an s orbital. So remember, we can add or subtract, so we can do s plus s, or we can do s minus s. So we'll look at what the pictures look like for each of those options. So s orbitals are spherical. And they can be in phase, or they can be out of phase. So we'll do the bottom one first. If we have in-phase mixing, then the molecular orbital is going to look like all of the same phase orbital where the lobe encompasses both of those two nuclei, because this is a molecular orbital. And we know the electrons occupy the space between the two. And since there is electron density in this orbital overlapping with that internuclear axis that connects the two nuclei, we're going to classify this as a sigma bond, the strongest bond that we know. And because there is electron density in between the two nuclei, this is going to be a bonding orbital with low energy. Then we can look at what happens when we subtract this. So it's called destructive interference for a reason. When we make our new molecular orbital, there is going to be a new node right down the middle. Now let's write that up here, which we know is not going to contribute to a strong bond. So that new node is going to lie completely across the internuclear axis, right where we would have liked there to have been a bond. So this is the easiest way you can identify whether a molecular orbital is going to be bonding or anti-bonding, is if there's a node right down the middle, that has to be an anti-bonding orbital. So this is kind of a goofy looking orbital, but it basically looks something like this. The orbitals are out of phase, and there is no electron density in between the nuclei, so it is anti-bonding. And the way that we represent an anti-bonding orbital is we put a superscript star next to this the type of orbital. So this is going to be called a sigma star orbital because it is anti-bonding. And remember how we said that these have different energies. An anti-bonding orbital has higher energy, and a bonding orbital is going to have lower energy. So we can represent the energy of those orbitals by drawing these lines as we did for atoms. So these are going to be our molecular orbitals in the middle. We can carry those labels over. So this is going to be a sigma, and this is going to be sigma star. And sometimes we even include a superscript to tell us what kind of orbital it was made from mixing. So we mix together s orbitals to make this sigma orbital, and we mix together s orbitals to make this sigma star orbital. Oh, and let's not forget our axis. We always try and label our energy axis whenever we're making a graph. And the way that we're going to draw these molecular orbitals, we're going to add even a little bit more information. We're going to add more information about the atomic orbitals that these molecular orbitals were formed from. And we know that the atomic orbitals have intermediate energy, because one of those molecular orbitals should have been lower energy than it started, and one of them should have been higher energy than it started. And we're assuming that we're mixing two identical atoms, so the energies would be identical. So this is an s orbital, and so is the orbital on the other one. And when we are mixing two orbitals together, we represent that by drawing a dashed line towards the molecular orbital that they make. So both of those s orbitals mixed to form this low energy bonding orbital, and they also mix to form this high energy anti-bonding orbital. So this is called a molecular orbital diagram that we use to represent how much energy the orbitals had when they started and how much energy the orbitals had after they went through the molecular orbital machine. Okay, so this is our simplest type of sigma bonding, but remember when we talked about the ways we could form a sigma bond, we said there were different types of orbital overlap that we could use. There's many different types. So let's look at one more example. Let's look at what happens when we overlap two px orbitals. So we can add them and we can subtract them. In fact, we always do both. We always form one bonding and one anti-bonding orbital. So px orbitals lie along the internuclear axis, like so. There we go. So in our addition, in our in-phase mixing, we are going to line these up so that the orbital lobes with the same phase point towards each other. So we're going to pick one of the phases. I'm going to pick green. And I'm going to make sure that the lobes that are next to each other are both green. And then the other two lobes will be black, because remember, we have nodes here down the middle in a p orbital. And we always change phase when we pass over a node. So when we have in-phase mixing like this, we are going to end up with a bond. And basically, we take this area with in-phase mixing and we make that area bigger because it's constructive interference. And we take this area over here that isn't really pointing towards the other molecule, the other atom, and we make it a little bit smaller. So it's a little bit silly looking, but it roughly represents where the electrons might exist. So this is a different example of a sigma bonding orbital. The bonding orbital you make by overlapping two px orbitals. So now let's look at what happens when we subtract px orbitals. So in this case, we're going to have out of phase mixing. So we're purposely going to orient the orbitals so that two different phases are pointing at each other. So the green and the black phase are pointing at each other on the internuclear axis here. And this is not going to lead to good things. This is going to lead to anti-bonding, destruction of a bond. So remember that whenever we have an anti-bond, there's going to be a new node that appears right through the internuclear axis. And that's how we know it's going to be an anti-bonding orbital. And when we form this, we're going to emphasize how the internuclear axis portion of the orbitals is destroyed by drawing really small orbitals towards the inside and really large lobes towards the outside. And then we'll color them the same way that they were when we started the overlap. So the overlap is still on the internuclear axis, so we still call it a sigma bond, but we have destructively interfered here, so we'll put the star to indicate that it's an anti-bonding orbital that is formed by that subtraction. So every time we mix two orbitals together, we have to make two orbitals as a result, one bonding and one anti-bonding orbital. And let's show the energies of these. So we are going to have two molecular orbitals formed. So we'll write MOs here. Our sigma orbital formed from px atomic orbitals, and our sigma star anti-bonding orbital formed from px orbitals. And then we'll draw our atomic orbitals on the left and right. So there's a px orbital from this atom and a px orbital from the other atom. And because both of these p orbitals overlap to form a bonding and an anti-bonding, we draw lines from each of them, dashed lines going to each of those newly formed molecular orbitals. So the molecular orbitals go in the center of the picture, and the atomic orbitals go at the sides of the picture. So those aren't the only examples of sigma bonding. You can also overlap an s orbital with a p orbital. You can overlap an s orbital with any of the hybrid orbitals, sp3, sp2, sp. You can overlap two hybrid orbitals. There are many ways to do it. These are just two of the most commonly encountered examples in diatomic molecules. So in the next video, we will talk about what the orbital mixing looks like to form pi bonds.